morning. Buenos días. I am Jorge Sofo, professor of physics at the physics department here at Penn State, and I would like to welcome you. It's an honor and a privilege to welcome you to the fifth talk of the 2025 Ashtekar Lectures of Physics. This popular public winter series is now in the 31st year. The lecture series was started by Ashtekar in 1995, soon after he arrived at Penn State as director of the new research center that subsequently became the Institute for Gravitational and the Cosmos. It owes to the success of this series the tireless efforts and meticulous planning of Barbara Kennedy, who presided over the series during the first 25 years, making it one of the most successful science outreach events in central Pennsylvania. This year's lectures, titled 2025, the Year of the Quantum, explores how physics at the smallest scales impacts materials, human health, communications, and more. The series celebrates 100 years of quantum mechanics and the UNESCO International Year of Quantum Science and Technology, which was designed to recognize the worldwide importance of quantum science and the need for a wider awareness of its past and future. Today, and for one additional Saturday, we will hear from researchers on topics that explore the depth and breadth of quantum research at Penn State and beyond. So we humans, we are explorers. We see a mountain and we start wondering what is on the other side. We see a large amount of water, an expanse of water, and we build ships and machines to go beyond, to go where we cannot go with our natural tools, our legs or our hands. We also venture at some point into the small, another place where we cannot go. And going into the small, we discover, for example, at the beginning, germs. We build microscopes, and we discover that some of our illnesses are coming from these little creatures that we didn't know about them before. Actually, we kept venturing into the small, smaller and smaller. To our surprise, we discovered that the laws that we learned to love about how nature works at the large scale, it didn't work anymore. Everything was strange. We built devices to go further and further into the small and further into the smallest temperatures. We need to study this. And this exploration, in the same way that the exploration of new continents brought us goodies, treasures, and discoveries, this exploration into the small is also bringing us wonderful discoveries and things that affect our everyday life. It has been doing this probably without many of us noticing for 100 years. And this year, we celebrate 100 years of this quest. And it coincides also with this public awareness of the effects of quantum into something that we all have in our homes, and we didn't know we were going to have in our homes 10 years ago. A computer will revolutionize something that is affecting everything we do. Today I want to present you one of my favorite explorers of the small. Professor Jun Su from the Department of Physics will tell us about building a quantum information highway network with topological edge states. Professor Su is a professor of physics in our department. She earned her undergraduate degree at the University of Science and Technology of China in 1996. A PhD in physics from Columbia University in 2003. She was a postdoctoral fellow in Cornell, north from here, from 2003 to 2005. And in 2006, we were very lucky to have her joining us in the Department of Physics. She's currently, as I told you, a professor of physics and is a fellow of the American Physical Society. Her research interest focuses on understanding the new physics and device functionalities arising from quantum phenomena and low dimensions, and the control of new electronic degrees of freedom in nanoscale materials and devices. Her recent research projects explore the electronic properties of van der Waals materials, with a particular emphasis on electronics, topological, and quantum Hall effects. Following the lecture, graduate students Sanika Katkikar and Kathy Young will help moderate the question and answer session with June. You should have received a pen and a piece of paper when you arrived. Please write down your questions during the talk, and our students volunteer will collect them for the question and answer session. Now, please join me to welcome Junsu.
Thank you very much, Jorge, for this wonderful introduction. Can you hear me okay? Yeah, okay. All right, so my name is Junsu, as Jorge said. I'm a faculty in physics. I'm also a member of the Penn State Materials Research Institute, and also a member of the Penn State MERSEC and the 2D Crystal Consortium. Both of these are very large research centers funded by NSF so that we can work as teams to tackle some of the most difficult challenges. So I want to talk to you today about a few concepts which you may or may not have heard of that is in quantum mechanics. Topology, which is characterized as something that is robust. Edge states, these are highways that carry electron without dissipation. Quantum interconnects, something that we need in order to wire up our quantum computers, and something that we don't have a solution for at this point. And what we have done in our lab towards perhaps a platform of building such highways. So if you flip two coins, you get head or tail. So if you do it for two coins, you get four possibilities. Okay? Head, head, tail, tail, head, tail, tail, head. Each one is 25% if you didn't rig the coin. Okay? Now in quantum mechanics, you can prepare a state of two coins where if you flip them at the same time, you get a head, head, both of them are heads, or a tail, tail, and you only get these two outcomes. So that is a possible, that's a state that represents this outcome. Okay? And the reason you don't get head, tail is I have established some sort of connection between the two coins so that they always appear with the same side. Okay? So here comes the funny part. If you now toss these two coins simultaneously, but keep them really far apart from each other, when one coin presents head, the other one would also present head. See, that's the only possible outcome. Okay? And this doesn't matter how far apart they are. And they're not talking to each other. Maybe they're too far to talk to each other. How does the system know one of them is giving a head, and therefore the other one should also give a head? Okay. So when quantum mechanics was first discovered, Einstein called this spooky action at a distance, and it's one of the least favorite part of sort of about quantum mechanics. Okay. This is what we call quantum entanglement, and it's a key property of quantum mechanics that allows us to exponentially speed up the algorithms. And that is a key advantage of quantum computing, is coming from this quantum entanglement. In fact, experiments have tested over and over again. You can put a photon, light particle, one in space on the satellite, one on ground, and they're still entangled. Okay? So quantum entanglement is very important for the quantum applications. Now, you have been to last week's lecture, Dr. Abhinav Kandada from IBM. You probably heard about error correction, how to actually compute without being bogged by errors. And that's because quantum computers are more prone to errors than classical computers. This quantum entanglement that is key is also something that's very fragile. We need to protect it by cooling down to very low temperatures, isolating it from the noise in the environment, cosmic rays, so on and so forth. Anything we know classical is going to ruin it, and we lose the advantage of quantum computing. Okay? This is very doable, and that's what people are working on. But then that makes you wonder, really, is quantum so fragile? Is there something in quantum mechanics that is a robust phenomena that we can make use of? Okay? Okay. And the answer is that there is. They are called the topological states of matter. And this was recognized by the Nobel Prize in Physics in 2016. And this is the first thing I want to tell you about topology in quantum mechanics and why it makes a certain phenomena very robust. So to talk about that, we have to go to the very beginning, 1980s. In fact, we're going to go 100 years even before that, 1880s, to talk about a phenomenon called the Hall effect. So the Hall effect, if you take a material, make a bar out of it, you pass a current this way, and if you put it in a magnetic field, the electrons feel a Lorentz force, and they're going to veer one side. And then you build up a voltage that's transverse to the bar. So this is known as the Hall voltage. Edwin Hall discovered this 1878, so more than 100 years ago. Okay? So the Hall voltage depends on a couple of things. It depends on how many charge you have in this plane, which is here. And it also depends on the magnetic field you apply. It is linear in the magnetic field you applied. Right? But if you look at this, there is nothing abrupt about it. It smoothly changes with B, and it smoothly changes with the charge density. Okay? So the surprise came in 1980 when Klaus von Klitzing did this experiment with a piece of silicon. He cooled it down, applied a magnetic field. This is a busy plot, but I want you to look at this curve. You can see 1, 2, 3 steps. Where did the steps come from? It's not in the expression, right? So this came as a big surprise, and nowadays we understand that these steps, in fact, are quantized, meaning having a very precise value, to a combination of fundamental constants, h over e squared. H is Planck's constant, E is the elementary charge, and then 1 over an integer. So that is 2, 3, 4, the steps that you see over there. Okay. So this was so out of the blue that Klaus was recognized with the Nobel Prize in 1985, quite soon after he discovered this phenomena. Okay. So this combination of h over e squared is now called the von Klitzing constant. And it can be measured with higher and higher precision. You can see there's 10 digits on screen here, and this is getting better and better. And this has been the standard of resistance since 1990. If you go to NIST website, this is what you get. Okay? It replaced the wire ohm that we used to use as a resistance standard. Right? So something that is pure intellectual curiosity is now having huge impact, especially on metrology. There is another one called the Josephson constant, which also arises from fundamental phenomena of superconductivity, which is 2e over h. That can also be precisely measured. And if you could do two of them, you look at it, a couple lines of algebra, you get the Planck's constant and the elementary charge, right? By just multiply and divide. Okay. So people probably know that we have international system units. And mass used to be this hunk of metal in vacuum, kept at a constant temperature, and so on and so forth. So this used to be the kilogram, the standard mass. Okay? Now, because these fundamental units are connected, since 2019, all these 7 units, fundamental units, have been redefined by fundamental phenomena, such as the quantum Hall effect and the Josephson effect. So in particular, mass is related to the Planck's constant because mc squared energy is related to h nu, the photon energy. So if one knows h very accurately, one could also measure the mass very accurately. And this was done in a device called the Watt. Now these days it's called the Kibble balance. On one side, this is a museum version, right? So on one side, it's a balance. On one side, you have an electrical force, and that takes into account the quantum Hall and the Josephson effect. On the other side, you have the gravity of a mass. And by using a device like this, you can accurately measure the mass and redefine what we call a kilogram. Now it's called the electronic kilogram. Right? In fact, this is a real version of this, the Planck balance. And this was a vision of Max Planck back in 1900. Max Planck was a founder of quantum mechanics. At that point, he said, with the help of fundamental constants, we have the possibility of establishing units of length, time, mass, and temperature, which necessarily retain their significance for all cultures, even unearthly and non-human ones. Not sure about the last part over here, but certainly for all humanity, we now have fundamental constants given by fundamental physical phenomena. Right? This was 100 years ago. You know what's the most remarkable part of this? Is that such data comes from a sample that might look like that. Okay. So this is a gallium arsenide Hall bar that I showed you. These are scratched by hand. You don't need precision. Okay. And these are contacts put on by, my graduate students can do better job than this. These are put down by, I don't know, right? So something so imprecise can give rise to the precise quantum Hall resistance that I showed you. Okay. So when I was a graduate student, I started working on related phenomena called a fractional quantum Hall effect in a sample that looks like this. And I still remember the feeling. I put in one of these in a cryostat, cool it down, apply a magnetic field, and there's this trace coming on screen that's just absolutely flat. And it's not because my locking amplifier is overloading. Right? The feeling, I think it's no less awe-inspiring than you stand in front of Grand Canyon and look at what nature made. Right? So something like this, exactly what's going on in physics. The origin of that is what we call topological phenomena in quantum mechanics. The analogy of that is some people, if you know geometry, you may know something called the Janus number that tells you how many holes does a surface have. A mug and a donut have the same Janus number. It's 1 here, and you can smoothly change a mug into a donut without changing the number of holes. Okay. So we're talking about physics. We're talking about electronic bands. There is an equivalent to that Janus number. It's called the Chern number in physics. This is something that doesn't depend on the details of your sample, size, dimension, and so on and so forth. Okay. In order to change that number, you have to make some drastic changes, and that's what that pow is supposed to tell you. Pow, a new hole occurred. Pow, another new hole occurred. Okay. When you change the number of holes in the material, something drastically changed. And that is shown here. The resistance, the steps that you see are as a result of the different numbers of holes we changed in the sample, different number of Chern numbers. That gives rises to these. And because it only has to do with the number of holes and not any other minor details, these are incredibly robust. These are quantized values of the sample. There is a microscopic way of looking at it, and that is to say that these materials, the quantum Hall samples, have a topological invariant number that is not zero, non-trivial. Our vacuum is a trivial one, has zero. And therefore, at the edge between the vacuum and your sample, and that's the edge of the sample, you now have what's called edge states. As a result of that non-trivial topology, if the difference is 2, you have 2 sets of edge states, and these edge states are like really good freeways. Once you pay the toll, the old freeways, you will slow down at the toll booth, that's the contacts. You drop some resistance there, but once you're on the highway, you travel ballistically without resistance again. So these are the marvelous properties of the edge states, and they come out of quantum Hall effect. Right? So we now have quantum wires that can carry electron ballistically without resistance as a result of the quantum Hall effect. This is probably not so hard to imagine, right? Number one, why do you use wires? Well, wires are a lot better than 2D. There's just many ways of colliding in a 2D plane. So if you do roads, one-dimensional roads, that's a lot better. And it's even better if you can separate the traffic in opposite directions, right? Okay. So this is the edge states of the quantum Hall effect. You notice that I have 2 ways of defining the traffic, either clockwise or counterclockwise. And that's given by the direction of the magnetic field. Okay? And that's why they're called chiral, because there is a handedness to the way the rules worked. Okay? So these are the best quantum wires that one could make in terms of reducing resistance of the electrons. Okay, so I want to switch gears and tell you a little bit about the challenges of quantum computing. Okay? So you probably have heard a lot of this in the news. Last week's speaker talked about this. From IBM, IBM announced the first more than 100 qubit system that's on the cloud. You can, in fact, access it and play with it. And this was already back a few years ago. And you very often see a picture that looks like that. That is not a quantum computer. That is called a dilution refrigerator. It is the workhorse equipment that allows one to cool down those qubits so that it could preserve this precious quantum entanglement that I told you about. Okay. And look how many wires it has. Okay. It has this many wires because a current day superconducting qubit chip looks like so. And mostly you see this meandering lines, those are superconducting waveguides. Okay. And every qubit has its own readout and control lines, which is why to host 100 of them, you need this forest of wires. Okay. Okay. So it's deja vu, maybe? Okay. Right? Okay. So you know quantum computing is in its beginning. Just right, look at the infrastructure around it. This is the first generation vacuum tube-based computers, code breaking in the World War II and so on. Okay? So you know, if history is any guidance, we're going to move away from this and perhaps move towards what silicon industry is these days, right? High-density packing, integrated circuits. So some companies recognize that, and university recognize that. Why don't we do this in a semiconductor platform? Because we already know how to scale semiconductors. We have a lot of existing technology to build on. So Intel, and led by Intel, other companies, universities as well, released something in 2023. And this is 12 qubits all in a row here, built on a silicon platform. Okay. This is already so sophisticated, the university clean rooms can't do this kind of thing anymore, not to the degree that you would want for a quantum computer. So they build this and then say, here, you guys test this. So released it to the community for testing in 2023. And these are some of the electron and transmission and electron micrographs. And you can see right away the scale of how small these things are. So it should be pretty clear that a semiconductor platform has a scaling advantage if you are able to build many more of these on a wafer. Okay? But you can't really use this geometry though, right? How many can you do? You are in a line. Okay? So you need to develop some other architecture that could take advantage of this. And such architecture already exists. This is how silicon industry marched from transistors, right? Bulky transistors into, these days, down to 2 nanometer nodes. Okay? You can pile up 15 billion of these on the size of my fingernail. Okay? But very importantly, you need to develop a way of talking to them, connecting the devices, then connecting blocks of circuits, connecting from chip to chip. Okay? So that technology, these bars that you see over here, are what we call interconnects. Interconnects was developed by IBM starting from the 1970s, first using aluminum, and then 20 years later, copper came in, because copper conducts better than aluminum. And copper is the standard of silicon interconnects in all your chips, basically. And if you look at one of these, this is already an outdated chip. A chip like this packed more than 10 billion transistors, but also 15 layers of these interconnects that does the job of connecting, control, readout, multiplexing, so you don't need every wire for every transistor, right? And if you want to shrink the density increase the packing density of transistors, you also have to shrink the size of these wires as well, right? And when you do that, you know if your wire has a smaller diameter, its resistance increases. So there is more and more power dissipated in this interconnect. In fact, 50% of the power of a chip generally goes to the interconnects. Okay. Because copper is not a superconductor. You can make it very conductive, but you cannot eliminate all of the conductance. Okay. So how to design these interconnects is very much the frontier of semiconductor industry. But you know that you can't really take this and wire up quantum computers with it because it's going to dissipate energy. Okay? It will never become a superconductor. So we have a challenge. Okay? We need something that does the job of the interconnects in a classical computer. And very crucially, it has to preserve this coherence and entanglement that is very much the advantage of quantum computing. And if you dissipate heat, heat increases disorder, you lose that entanglement. Okay. So, and all the nice things that we like about the classical interconnects, we want it to scale, we want it to do signal multiplexing. Do we have a solution? Okay. The answer is we don't at this point. But there are many things that are being worked on. One of the things, for example, that's being worked on by the semiconductor qubit community is to connect them via microwave waveguides, superconducting microwave waveguides. Right? Okay. So again, research front, right? You notice a couple of things, right? Number one, it works good. Number two, how small the qubits themselves are and how long the wire in between is. You look at the scale bar here, right? So why? Because you're using microwave. Microwave has gigahertz frequency and wavelengths on the order of maybe half a foot. Just think about the size of the microwave we have in the kitchen. Okay. So if you do that, you can't really shrink the size of the waveguide. Okay. So you're losing some of the advantages of semiconductor platform. You can't really pack them that dense anymore. Okay. Okay. So is there another solution? Right? Anyone? Edge. Thank you very much. Right. How about we wire up quantum computers with the edge states of what I just told you about? Because they are wonderful quantum wires, and you can carry electron without resistance, right? So good. So you checked out these two, but there's a bummer here. Bummer is the effect I told you about, need a strong magnetic field. In quantum computers, qubits don't like magnetic field. It interferes with how they work. Right? So can you make edge states at zero magnetic field? Okay. Okay. Right. Okay. So in the remaining of the talk, I want to tell you about how you might make edge states at zero magnetic field. And perhaps from there, how you can, I'm going to show you 1 wire, or 2 wire, or 3 wire, 4 wire. I want to use your imagination to extrapolate to an entire wafer of network. Okay. But this happens all the time. In universities, we do single device, a few devices. So long as the proof of principle works, industry takes it and then cover the entire wafer with it. Okay? Okay. So in my lab, we have shown that indeed one can create these edge states, and they can carry flow of electrons without resistance. We can do more than that. We made a switch so that you can start controlling the flow with an electrical signal. Right? We like that because we're making a chip. We don't want to shine light on it in order to switch on your TV, right? You want to click a button that sends an electrical signal. And I want to show you some of the cool sort of traffic control, signal routing, wave guiding that we can already do with a system like this. Right. So the material that we built these devices on is called a graphene. And graphene is about 20 years old at this point. Okay. It is one sheet of carbon atoms, just carbon, arranged in this honeycomb lattice. Okay. It was discovered about 20 years ago, and these two gentlemen, Dr. Andrei Geim and Konstantin Novoselov, were awarded the Nobel Prize also quite quickly. Okay. Graphene is marvelous. In fact, maybe your tennis racket already has it. You just didn't know about it. Right? It's very light, but very strong. It's 100 times stronger than steel. And it is now being used in airplane construction. Light, strong, more fuel efficient. It conducts, so you even get a Faraday cage to shield you from the lightning. Right? We use metal for that, but graphite adding to it makes it lighter and still does the same job. It's very bendable. Okay? It's very flexible. It's transparent to light. So one could make a touch screen. Samsung has made touch screen out of this. And wearable electronics, flexible ones. So I don't know when this was a prototype exhibited. Whether it hits market depends on a lot of things, right? Economics and so on and so forth. But that's another thing graphene could impact. People have made sensors for medical purposes out of graphene that you can wear on your wrist. Again, because it conducts very well and it mixes very well, you can put this into lithium battery, and it's a wonderful anode in lithium batteries. Okay. And what's also good about it is that these days we know how to make it on a large scale. Okay. One could grow this. A lot of my colleagues at Penn State here do growth of graphene and similar 2D materials using CVD, chemical vapor deposition, epigraphene, epitaxial growth, and so on and so forth. If you can make this en masse, there is a market. There's commercial applications for it. So this was a market projection, best scenario, minimum scenario, average scenario. You can see that this is 2,000 millions. This is $2 billion in a few years. Right? It's still very, very small compared to silicon, but it is turning research into applications and products. So I want to talk about another exotic properties of graphene that has to do with topology. And that's the fact that electrons in graphene have two valleys. Okay. What does that mean? Because your hexagon has 2 atoms per unit cell, that means there are 2 ways of doing a lot of things. Okay. So this valley is what we call an internal degree of freedom, just like the spin of electrons. How many people have heard of spin? Okay, some. It's how your hard drive works. That's why things are magnetic. Iron has a lot of spins lined up in the same way, right? So you may not know, but you're already making use of it in a lot of our applications. Now, valley is a different one. It just looks like spin. In this graph, it's shown by these loops with 2 different colors. Right? In fact, researchers have made qubits in graphene using this valley as your 0 and 1 state. 2 states, you can make a qubit. It can be spin, it can be valley, it can be other things. Okay. But I'm going to think of them as colors for electrons. If an electron occupies the K valley, which is one of the 2, I'm going to say they're blue cars. And if they occupy the K prime valley, the other one, I'm going to represent them with red cars. Electrons don't have colors. This is just a way of separating sort of the 2 flavors of electrons we have. Right. And I work with a material called bilayer graphene, which is take 2 sheets of graphene and then stack them on top of each other. What is particularly interesting about bilayer graphene is if you apply an electric field perpendicular through the 2 sheets, you open what's called a band gap. And band gap is very important for how semiconductors work. Okay. So bilayer graphene has a band gap that's controlled by the electric field. We take a graphite crystal, we take a Scotch tape, we get some of that flakes on a Scotch tape, you fold it a couple of times, just like pretending you're making pastry, and then you put it down on a silicon wafer, and then voila, oops, you get flakes that look like this. You can see them in an optical microscope because it changes the color contrast very slightly. Right? That's 2 layers of graphene right there on the wafer. It's not very big because they came out of this. Right? But it's big enough to get us started to do research on it. And then we go to the clean room in the MRI, the Millennium Science Complex building. Right? In fact, Penn State has one of the best university clean rooms of the entire country. State-of-the-art equipment, we have everything we need to make devices. This is a fun tour that you can find on YouTube and see what's inside. So my students go in and they come out with something that looks like that. So this is a SEM, scanning electron micrograph of one of the devices that we made. They don't have colors, we colored them. Right? Graphene is not purple. But this is just to show the structure of the devices that you don't make. And notice that there is a tiny little gap in here, and that gap is 70 nanometers. This is where our edge states live. They live inside that channel. This is where we're carrying the current flow. So this device allows us to do the following. Okay. So remember the electric field I told you about that opened a gap? So we pointed one way on one side of the sample, then the other way on the other side of the sample, like this. Okay. So you opened a gap on the left, you open a gap on the right, but I also made a twist to the band structure. This also opens 2 gaps, no twist. This has a twist. This also has a twist. Okay? Okay. So by creating this twist in the band structure, I have created the edge states that we discussed before. But I don't need magnetic field in this case. Okay? Okay. And in fact, these edge states I told you about have an interesting property, and that is if you look at the blue electrons, they go one way, and the red electrons go the opposite way. So I have linked the color or the valley, the quantum degree of freedom that graphene has with the direction the electron is going. In other words, I've created a set of rules on how my highways look like. If you are a red car, you can only go in the red car lane, and that also says you can only go in a certain direction. Okay. So this was predicted back in 2008 that if you could do this, you will get these edge states, and wonderful things will happen. So why is color good? Why is color-coded highways good? Because now, if I'm a blue car and I want to turn around and go the opposite direction, I need to change the color. Remember, they're color-coded, right? So turn around meaning scattering, meaning resistance. Changing the color meaning going from one valley to the opposite valley, right? So if you can remove all the processes that allows the electron to change the color, then you forbid them to go into the opposite direction. Then you eliminate the resistance of the wire. Okay? You see, color coding gives a way of controlling this process. Okay. So this is easily said, but difficult to do. It took 2 generations of graduate students to figure out how to actually eliminate all the processes that could allow the electron to change its color. Okay? But we finally got it. And the proof is in this flat part that you've ever seen before. This is step. So this step is quantized to h/4e squared. It's not nearly as good as the von Klitzing constant because this is the first experiment. Right? And it could be better, but it already tells you that now there is a ballistic wire that can carry electrons, and we don't need a magnetic field for this. Why stop there? We just made the road. Let's make something else. Okay? So we made a switch. So a switch chops current, turns current on and off. Okay? Okay. If you do this with silicon electronics, this is how a MOSFET switch works. You use a gate and you deplete or enhance carriers between your source and drain. If you don't have carriers there, current stops flowing. Okay? So that's how you turn it on and off. Okay? So we made a topological switch. What does that mean? So in this state, we have a twist. I have these rods. Right? It conducts perfectly. And then let's do the other configuration where there's no twist. There's no twist, there's no edge states, and therefore there's no conduction because there's no road. The state itself disappears. Can you imagine you get to a toll booth, there's no road in front of you? Right? So this is something that we control with voltage signals. Okay? So as a result of that, you get on, off, just flipping, right? So it's a new kind of switch, topological switch, because we're controlling the topology of the system, not the amount of carriers we put in it. Right? Okay, so we have a switch. Switch is important. If you're making a network, you need to be able to stop the current flow at some point. Okay? We did something else. We made a cross junction, intersection with 4 roads. Okay. So now this road is designed in such a way, if you look a little bit carefully, you see the rule of the road. Right? Blue car go this way, red car go that way. On the other side, it's switched. The red car go this way and blue car go that way. Again, this is by controlling how I twist. One way, other way. Right? Okay. What does this do? If you're a blue car, you come over here, and you look across to the other side, you realize in order to move forward, you have to change your color. And we just eliminated all the processes that could allow an electron to change the color. So as a result of that, this electron cannot go, okay? Cannot go. This one also cannot go because it encounters the same problem. Neither could these because my roads are built in such a way. Okay? So we made a valve that turns off the current flow by controlling, again, the topology, the color coding of the system at this four-way junction. Right? So where does this car go if it can't go forward? You can go right or you can go left. Right? And which way does it go depends on, well, which side is closer. In physics language, which side does the wave function overlap more? If it overlaps more with the wave function on this side, it will preferentially turn right, otherwise it will go left. And we have a knob that controls how much this coupling changes as we turn this knob. So as a result of that, we can control from 0 to 100% whether the electron turns left or right, probability-wise. Okay? Okay. So that's how a device like this looks like. This is a four-way junction. You recognize the cross. Okay. This is a zoom in of the cross. And you can see that our roads are very narrow and they're very short. Okay. They're 65 nanometer features. Again, without the tool in the nanofab, none of this would be possible. You can pack a lot of these on a wafer if you know what you're doing. Okay? So the scaling advantage of doing a semiconductor system is also here. Everything, the approach we've taken so far is the semiconductor technology. We are patterning using lithography to define features and so on, using gates to manipulate and so on and so forth. And when we send a current, when we send a current through one of the roads, say the current comes in from the south, the electron comes from the south, and you can see that the north part, this part, gets very little current. This is less than 5%. The valve is not perfect, but it's working. And if you see the current that we get from the west terminal and the east terminal, you see this X. In this part, all of the current goes to the east terminal. The west terminal has almost 0. But with the control of the knob we have, we can make this switch. We made a tunable beam splitter that tunes the beam splitting of the electron. Okay. In quantum mechanical language, we change the probability. The electron is going to be a superposition of going left versus going right, but we are controlling the probability of these two choices. Right? Okay. So this is how far we've gone. We've made these roads, color-coded roads of electrons, where the Valley degree of freedom, hence valleytronics, is linked to the direction it's going. Okay. And these are wonderful quantum wires because they belong to the kind of topological class, edge states, not just a wire etched out of a piece of metal. Okay. There is an underlying topology that makes them very robust against the resistance. Okay. And we've shown that's indeed what's happening in our experiment. Okay. Now, this is one road. This is one cross junction. Okay. Okay. So with one cross junction, we can already show a bunch of things. We know how to direct traffic. So we can route signal in a structure like this. Okay. We know how to turn them on and off. Okay. So this is pretty far away from having a network. Okay. One road, one cross junction. You go to a village, you go to a city. There's a lot more roads to build and also rules to decide on how do you lay out the city and what are your traffic controlling rules and so on and so forth. But I hope you begin to see that maybe this has a shot because it has some of the key properties that we're looking for in a quantum interconnect network. Okay. So for us who are doing fundamental science, the next steps are these fundamental questions. So I've talked to you about how our states can carry current without resistance. Does it preserve quantum entanglement? We don't know. That's a key question that we need to answer with more experiments. Okay? How do we figure out how to operate these things? How do we operate the gates, equivalent of the classical gates, the quantum gates? How good is our devices? If we have error, how do you connect it? There's a whole bunch of scientific questions that we, who do fundamental research, need to figure out. But there's also materials challenges. Right? So I've shown you a monolayer graphene, one layer, graphene wafer on 6-inch that you can already buy from a commercial company. It turns out that doing the same thing for 2-layer growth is still very much a challenge, and it's a research problem. Okay? Until that happens, we can't really pack the wafer with the rods that I've shown you. Right? I'm working with 10-micron size flakes. Okay? Okay. How do you design them? If you had a large scale, right? Do you do this? Or do you do this? Okay. What is your architecture? Okay. How do you couple the qubits together? Okay. And that also impacts on how you would work. What does your algorithm look like? Hardware and algorithm, software, these days are very intimately connected. Okay. You want to design your chip in the right way so that it's optimized for the algorithm that you are going to carry out. Okay? So these things are all related. And then I'll get a company to go from here to here. Okay? This I'm least worried about because everything we've done so far is a scalable technique. Right? And maybe at some point we can talk about scalable quantum computing. But that's pretty far down the road. And because it's fundamental research, I don't have a roadmap. Okay? As you can tell, if you have a roadmap, it has gone into at least some in the regime of applied research and engineering. With fundamental research, we don't know whether, we know generally speaking which direction might yield interesting stuff. But what will you find? We don't know. Is it going to be useful? We don't know. Did you find a unicorn? Did you find a panda? We don't know. Need to check out. Right? So, but that's really the nature of fundamental research. And again, if you go back and think about quantum Hall effect, when it was first discovered, it was just a step. Right? Pure intellectual curiosity. And who would have thought that it is going to replace the kilogram and make the mass standard the way that it is these days? Right? Okay. So it's not going to be easy, but it's something worthwhile making an effort to. I want to thank my group members of the Zhu Lab. This is us at Bald Eagle. My collaborators from various places, Penn State, USTC, and also the National Institute of Material Science in Japan. Okay. The hero of the story is these two fellows, the two graduate students who worked out the challenges to make it a reality. Jing Li, who's now a faculty at Huazhong University of Science and Technology. Ke Huang, who just graduated and is now a postdoc at Cornell, Stanford. One of my other students went to Cornell. And also special thanks to the MRI Institute. Really, facilities like this make what we do happen. Right? This equipment that we use to build these devices are very expensive. You can't really have it in an individual PI's lab. So this is where these large-scale facilities come into play. And Penn State is a wonderful place for that. We have a very large materials program and all sorts of state-of-the-art facilities. Our funding agencies, NSF, DOE, our funding centers, the National Magna Lab, and finally, thank you for your attention. I'm happy to answer questions.
Thank Professor, for this wonderful talk. We are now going to take questions, but before that, I think I have a question for you. So you described all of these topological test states. What do you think is the biggest hurdle in manufacturing?
It probably depends on, so the question is, what is the biggest hurdle? It probably depends on what kind of edge states you're talking about. I talked about two kinds. The first one is the edge states of the quantum Hall effect, right? They occur at the edge of a sample. So if you want to make use of them, you have to think about the ways of etching your sample so that you can make use of the edges. That's not really that trivial, right? Okay. And also, that requires a magnetic field. So that's another thing you have to think about if you're thinking about making large scale. The ones that we discovered in our lab, these don't require magnetic field. And we're using lithography to pattern them. Okay? So it sounds easier. But right now, we only have materials that are 10 by 10 microns. It's very small. That already limits how many of them you can make, right? And I didn't show you all the tricks that we have to play in order to make those conductance quantize. That's 2 PhD students' work. This idea of, oh, let's just eliminate all the color changing processes requires really hard work of figuring out how to clean the material, how to optimize the devices, and so on. Okay? It is very challenging. And our roads are maybe 400 nanometers in size. If you make them 40 micron at this point, I can tell you that they're not ballistic because there are still something that is doing this scattering. And you really want to cover the entire wafer, you have to keep working on those problems.
Thank you so much for that answer. We have one more question here. This is fascinating. How does variability in the nanofabrication process affect the efficiency and or the efficacy of the switches you discussed? Switches you discussed.
Right. So again, this comes down to what you can do in a university clean room. Okay. So a lot of that variability comes from you want to evaporate, let's say, gold. The previous person in front of you, before you use that, evaporated nickel. And as a result of that, some of your gold now has nickel in it. And you may be looking at a process where you don't want nickel, because nickel is magnetic. Okay? What I'm trying to say is that university clean rooms are not controlled. The processes that go in, because we are exploring open problems, we need to allow students to do outrageous things, right? If you look at Intel's foundry, processes are, you can only do one thing in it, and they do extremely well. So that is how you can put 50 billion transistors on the wafer with enough yield that you can make what we make, right? But then you're stuck with that, right? You move to an industry process when you know something is working, and university is playing your role of figuring out what could potentially work, the open-ended exploration. So we suffer the uncertainty and variability. Right? Today the tool is working. Tomorrow I ran the same thing. It doesn't look the same. What happened? Okay. But that's part and parcel of what this process is.
Thank you so much. We have another question. How do your interconnects compare with the interconnects in classical, in short, conventional computers?
Right. So how do I compare? I don't. It's apples and oranges. Right? The classical interconnects are fantastic. They do a fantastic job in connecting your classical transistors and memories together. You can't really compete with them. Quantum computers are not there to replace classical computers. They're doing things that classical computers cannot do or cannot do so efficiently. My quantum connects, you're not going to use them if you want to connect silicon transistors. You're much better off sticking with copper. But if you're connecting qubits, copper does not work, because it doesn't preserve quantum entanglement. Okay? So you need a new technology, and that's where a lot of these basic research is going into, is to find that potential new technology.
Thank you so much. Just quickly checking, are there questions on Zoom? Any other questions in the audience?
It seems like there'd be a benefit. You mentioned that you have
Hold on.
I can tell you.
It seems like you mentioned, it seems like there's like lower resistivity in the states that you're, or the highways that you're building. And it seems like that would be a benefit on its own, even if you weren't using quantum states. Is that the case, or is it not the case that we have better conductivity in your circuits?
Right. Okay. So I glossed some details over when I told you about these highways. So it's true that when our electrons are on these edge states, they don't encounter resistance anymore. But remember I told you about the toll booth? That in order to be on the highway, you first have to slow down at the toll booth. Right? So what that actually means is that when these wires, they're not superconductors. When you enter it, at the contacts where they enter, it does have a resistance. And that resistance is governed by the von Klitzing constant. Von Klitzing constant is 25.8 kiloohms. It's not a very small resistance, right? So you pay the toll once, and then you can roam freely in that network. But that toll is pretty hefty. So if you compare to copper and just on the resistance-wise, and including that into account, it doesn't compare with copper. Can be 0.001 ohms and so on and so forth. Right? So, but what we are looking for is that's the readout process. Once you are in the network, you can do a lot more things without resistance inside it before you have to send your electron out for a readout. And that's where copper could never do. Okay.
I think we have a couple more. What other than computers could we use this technology for?
Excellent question. So quantum computer is really just a stand-in for any quantum device that you're thinking of. Right? Your silicon industry consists more than just processors, right? There are memories and so on and so forth, amplifiers, and all of this, if you're making a quantum version of it, and you would need a different interconnect. It's copper in silicon and gold in 3-5 semiconductors at this point, right? So long as you need to preserve that coherence and entanglement, you need to look for a different wire other than the traditional metals. And again, this is really, I don't know, we don't even have a thing that connecting the qubits yet. What do I know? But if you can connect qubits, you can connect memories and so on. Right?
Thank you. One last question, I think. What about the Microsoft quantum computer?
Oh, what? Who asked that last time? So what do you know about the Microsoft quantum computer? Right? They just had a news Nature article a week ago, right? And then there's this press release, right? So my students are very excited. We talk about it at the group meeting. One of them said, I'll do a journal club on what the science is. Right? But I looked a little bit into it. It's very interesting what the paper says, what they have achieved, versus what the press release of Microsoft says, what they have achieved. Okay. If you just read the press release, I think in very certain words, they say they are going to have topological quantum computers in years, not decades. Right? It's probably good for the stock of the company. Right? But if you read the papers, what it says is we have developed a new way of detecting what's called Majoranas, which is the fundamental thing that you needed to make the topological qubit work. And we're not so sure if what we saw is Majoranas, but it could be. Right. And if you, Nature has this interesting thing where you can go in and read the report of the referees. It's a scientific paper, it gets peer reviewed, you can read the reports of the referees, and there's, sort of encouragement and doubts and so on and so forth. And so is the response of the scientific community to what it is. It's a good step forward, but would you bet on Microsoft cranking out topological qubits in next? I won't. So right. But I think the key word there is topological, isn't it? Right? I think it works on the same idea that I've discussed, which is if you find something in quantum phenomena that's also topological, you can potentially get a lot more robustness out of it. So the idea behind what Microsoft is trying to build, that's different from what IBM is trying to build, is that their qubit makes use more of that entanglement that I spoke of, and use something that's called the non-local operations, which is this spooky action at a distance, and therefore can be potentially more robust against the classical world around it. So it is a very fascinating direction to go. And that's where fundamental research would go, to see whether this will actually lead to a real robust quantum computer down the road, right? But timeline, again, it's fundamental research. The very nature of it is that you don't have a roadmap. Okay? Anyone says they have a roadmap, you kind of,